Okay.
All right, so let's start our seminar today, which today is online. And it's our pleasure to introduce you to Mathieu Fradelizi, who's coming from Université Gustave Eiffel, which before was Paris, which before was Marne-la-Vallée. And he's going to talk about connections between information theory and convex geometry. So whenever you want, Mathieu.
Thank you, David, and thank you for the invitation. So yes, I will talk to you about this, and so let's start. So I will first talk to you about this analogy between information theory and Brunn-Minkowski theory, and I will show you two examples of analogous inequalities.
Estaré con el seminario porque este me interesa.
And then I will show you two conjectures on compact sets, concavity of entropy power and monotonicity of volume of Minkowski averages. And then four conjectures, or a few conjectures on convex sets and zonoids. So let's start with the beginning of this analogy. So there is this Brunn-Minkowski inequality for compact sets. So if you have two compact sets A and B in Rn, dimension n, then the volume of the Minkowski sum of A plus B to the power 1 over n is larger than the volume of A to the power 1 over n plus volume of B to the power 1 over n. So here I gave two examples of Minkowski sum. So Minkowski sum is just the sum of, you can define in any vector space. This is just the sum of points. So the set of small a plus small b with small a and in capital A and small b in capital B. Okay, all vector sums you can have. And so this is an example, the first one, and the second one, another example. So you get things larger, and you can you have this property of increasing of volume in this way. And the entropy power inequality is about information theory, and we have random vectors which are independent, x and y in Rn. Then the entropy power is n of x. Is n of x plus y is larger than n of x plus n of y. So if what is the definition of n of x? If x is distributed according to f, it has density f with respect to Lebesgue, then the n of x is exponential some power times the entropy, which is the usual entropy. H of x is minus integral of f log f. Okay, and there is another inequality which is very similar, which is a Brunn-Minkowski inequality for matrices. And this we teach to our students, and we have two non-negative, so it means symmetric non-negative matrices in our with dimension n, square matrices. Then the determinant of a plus b to the power 1 over n is larger than the determinant of a to the power 1 over n plus determinant of b to the power 1 over n. So there is a way of proving this inequality just by applying the entropy power inequality to Gaussian matrices with covariance matrix A and B. And then we recover exactly this because the entropy power of a Gaussian matrix is just the determinant of the covariance matrix. Very good. Also, there is a way to recover the Brunn-Minkowski inequality for matrices from the Brunn-Minkowski inequality for compact sets, but it's not completely direct, but it works. And so we have these analogous inequalities, and in fact, it's not, there is a deep connection between these inequalities. This is not a random analogy. This is because, in fact, they both come from the same Sharp-Young's convolution inequality. So let me explain this. So you have the Young convolution inequality is you compare the LR norm of the convolution of two functions f and g with the LP norm of f and the LQ norm of g, where p, q, r are linked by the relation 1 over p plus 1 over q is 1 plus 1 over r. And so the usual Young's inequality that we can prove in class also is just with constant 1, and it's not difficult. But this one with sharp constants was proved by Beckner and Braskamp-Lieb in the 70s. And it's a bit more difficult to prove. It's a real advanced analysis. And this sharp constant is rich for Gaussians. And the constant here is given by, so here is the formula. And as usual, like in Minkowski inequality or Hölder inequality, if P, Q, and R are smaller than 1, then the inequality is reversed, and you do it only for F and G with positive values. Okay, and there is a way to rewrite these inequalities in terms of what is called Rényi entropy power. So this was done by Cover, and so if you have, what is the definition of Rényi entropy power? So again, you have a random vector in Rn with density F. So the Rényi entropy power is just the power of some power of the LR norm of F. Okay, so it's just matter of normalization if you want. You just define this, and but there is a nice way to rewrite this in, because of course the Young's inequality is about convolution. Convolution of densities is just the density of the sum, and so there is a nice way to rewrite the inequality, Young's optimal inequality, in terms of NR. So first, before writing this, let's notice that for R equals 0, or tending to 0 if you prefer, this NR is N0 is just the volume of the support of F to the power 2 over N. For R tends to 1, this tends to integral of F log F, and this to some exponential, and you recover exactly the entropy power. And for R tends to infinity, this is some power of the maximum supremum norm. Okay, and so reformulation of Sharp-Young's inequality was done by Dembo, and it is that the NR, the entropy power, the Rényi entropy power, the R Rényi entropy power of a sum of independent random vectors, variables, is larger than some constant, again, times the NP of X to some power, NQ of Y to some power. And now if you do some limiting case when PQR tends to 1, you exactly recover the entropy power inequality. And when PQR tends to 0, this gives the Brunn-Minkowski inequality. So Brunn-Minkowski entropy power are both some kind of endpoint of the same inequality, which will be this one, the Sharp-Young's inequality in the form of Rényi entropy power. And so you have...
sorry.
Yes?
Yeah, sorry.
Yes.
Yeah, when you mean reformulation, is it just curiosity? Is it reformulation or it's a theorem?
It's completely a reformulation. It's direct.
It's just okay.
Yes, yes. It's because this NR, NP, and NQ has just some power of the LP norm, LQ norm, and LR norm.
What they have to be okay.
And so you need to adjust, but this is exactly a rewriting. But in this form, you see that there is this link because N1 is N, and N0 is volume of the support. And so you recover, and if you have two random variables, their support is just the sum of the support. The support of the sum, sorry, is the sum of the support. And so you see that you can get this inequality, but from this one, which is just Young's inequality. But don't hesitate to interrupt me if I am not clear or if you need more precision or anything. I'll be glad to explain. Very good.
Okay, thanks.
And so this is this analogy. And so in fact, there is more. Usually and in this talk also, I will speak only about this analogy, but you see that there is a whole family in between that we could think of. And so there is a very rich source of possible inequality to prove when you want to pass from one world to the other. So for example, the isoperimetric. So the isoperimetric, there is no problem, it will work for all R's. The isoperimetric inequality, so let me show it to you. So you know it, and here is the drawing. So if you have a compact set in Rn, we define, let's define f of epsilon is the volume of A plus epsilon B to n to the power 1 over n, where B2n is just the Euclidean ball of radius 1. So here is some Euclidean norm. And Brunn-Minkowski inequality, if you apply it with A and B, with A being A and B being epsilon B2n, because the volume is n homogeneous, you get exactly f of epsilon larger than f of 0, okay, plus epsilon volume of B2n to the power 1 over n. This is what you get. And so if you take ff, you can rewrite it as f of epsilon minus f of 0 divided by epsilon is larger than volume of B2n to the power 1 over n. And when epsilon tends to 0, you get that the derivative, if there is a derivative, the derivative will be larger than volume of B2n to the power 1 over n. So this is really direct consequence of Brunn-Minkowski inequality, which gives you this. But what is the derivative of this function f of epsilon? When you look at it, volume of A plus epsilon B2n to the power 1 over n, when you differentiate it, you get this 1 over n, which comes out, and then the derivative of volume of A plus epsilon B2n at 0, and then this volume to the power 1 over n minus 1, because you take it at 0. So if you rewrite it, you get exactly this inequality that I put in red. And because the derivative, what is the derivative of the function, just the same function without the power 1 over n? This derivative is just, you look, A plus epsilon B2n is just an epsilon neighborhood of A. Here I draw this picture. I took it, in fact, these first pictures, I took it from Artem Zwavich's talks. So maybe you have already seen it, because I've seen that he talked also in your seminar. And so this is an epsilon neighborhood of A. And if you do the derivative, it's just, again, the same thing. You look at the epsilon neighborhood of A, you look at the volume, you take minus volume of A. So this is like the volume of the corn around this thing around, and you divide by epsilon, and you get exactly some definition. This is a Minkowski measure of the boundary of A. So here I denote this way. This is a Minkowski measure of the boundary of A, and the definition is just the lim sup or the lim inf, I forgot. You can take both of there is upper and lower Minkowski measurement of this limit. Okay, so this is isoperimetric inequality. And this is exactly the usual isoperimetric inequality, which says that if you have two sets, if you have a set with fixed volume, the surface array is minimized if you take a Euclidean ball. Here, it's not difficult to check that in all inequalities I have used, there is equality if A is a Euclidean ball. So there is an equality in the limit too. And you can say it also to respect more the word isoperimetric. Isoperimetric means same perimeter. So among sets with same perimeter, which means same surface area here, the volume is maximized if you have the Euclidean ball. So if you have, you feel it. This is like more like bubbles. Okay. So this is the classical isoperimetric inequality for compact sets. And I recall the Brunn-Minkowski inequality was valid for compact sets, so it works. In the same way, in fact, starting from entropy power inequality, which I denote by EPI, you can, because the entropy power is not n homogeneous, but is 2 homogeneous. When you look at n of square root of epsilon z, this is just epsilon n of z. And so when you apply entropy power inequality to a random vector x and a standard independent Gaussian vector z, dilated by square root epsilon, you get f of epsilon is larger than f of 0 plus epsilon n of z. So you can do exactly the same game. You do f of epsilon minus f of 0, you divide by epsilon, epsilon tends to 0, and you get that f prime of 0 is larger than n of z. And now you need to see what is f prime of 0. So this is the derivative of this function. And in fact, we know the derivative of the entropy. So the entropy, the derivative of the entropy up to a terms 2 is just the Fisher information of x. And the Fisher information, it can be written also in terms of the integral of the derivative of the density and the density. So this is the formula. And so if you apply this, we differentiate. So we had f prime of 0 to compute. So you get 2 over n, you get this factor, and the derivative of h times, again, n. So and the derivative of this is just I of x. And there is a 2, but there were 2 over n, so the 2 cancels out. And we get exactly I of x times n of x is larger than n times the entropy power of the Gaussian. And in fact, you can, it's not easy to see it this way, but this is a form of logarithmic Sobolev inequality. Okay. You can do also the same with the Brunn-Minkowski inequality for matrices. So here, notice we applied the second body was epsilon b to n. Here, the Euclidean ball is replaced by Gaussian vector. For matrices, it's common to take identity. So we will take epsilon identity. We could apply it to any, I mean, we can apply it to many matrices. So let's apply it to epsilon identity. So for Brunn-Minkowski inequality for determinants, we get again the same inequality. And if we differentiate, we get f prime of 0 larger than 1. And if we want to compute what is this derivative at 0, we get 1 over n again, the derivative of this determinant. And this is easy because this is an n linear form. It's easy to expand. And what are the derivative? This is just the sum of the minor, ith principal minor of A. And so you could argue that the isoperimetric inequality among positive non-negative matrices is this inequality. Okay, very good. So this is kind of surface area of the matrix, and this is kind of volume of the matrix. Very good. So this was the consequence of Brunn-Minkowski, but there are other inequalities. So the game now will be almost in all the rest. In fact, there are many more inequalities that are known in the world of information theory than in the world of convex geometry. And so we will start always by some inequality which is known in the world of information theory. And we try to see if the same analog inequality is true in the world of Brunn-Minkowski inequality. So for example, we start with the concavity of entropy power, which says that this T maps to, so if you start with X, which is a random vector, and Z, which is an independent Gaussian vector again, then this map is concave. So this is the concavity of entropy power, which is what's proved by Costa and Cover. And they conjectured that the same hold in the world of compact sets. So is it true that the volume, if you add, so you are looking at this T neighborhood of a set A, but T is moving, and you look at this volume and you ask if it is concave, this power 1 over n. Okay, so this conjecture, this is not difficult to see that Brunn-Minkowski implies that this conjecture holds for A being convex. And for A being any compact set, this we studied with my PhD student Arnaud Marsiglietti when he was with me here in 2014. And this was his first paper. And we could prove that the conjecture holds true in dimension 1, holds true also in dimension 2 for A connected, and also in dimension n if A is just a finite set of points and T is large enough. But it is false in dimension 2 for non-connected, I mean for some non-connected A, and it's false in general. So you need to have, and it will be always the case, in fact, that these conjectures are always a bit stronger, and you need to have more hypotheses. So the question which hypothesis you should add so is very interesting and leads to many other conjectures. So for example, there is this question that we left open in this paper and nothing was done since, I think, is that is it true that if you start from a compact set A, if you take T large enough, for example, T larger than diameter, then for T larger than this map is concave. So we conjecture that it is true, and we could not prove it, but it seems on all examples we were looking at, it was true. So this is a question. Another thing that we studied is monotonicity of entropy and volume. So it was proved by Hartstein, Ball-Bartnauer in 2004 that if you have a sequence of IID random vectors, yes, then the entropy that I already defined of the normalized sum of these vectors is increasing in M. Okay, and this was part of I mean, this was natural to guess because the entropy we know is maximal for Gaussian, and we know from central limit theorem that this tends to Gaussian in some different ways. And so also it was proved before that the entropy of this tends to the entropy of the Gaussian. And so the question of is it standing monotonically, in a monotone way, was natural, and it was proved by Hartstein, Ball-Bartnauer that it is the case. And Bobkov, Madiman, and Wang ask if the same holds in the world of Minkowski sums. So for compact sets, we defined A of M, which is some average, Minkowski average of A. Is it true that volume of A of M is smaller than volume of A of M plus 1? Is it increasing, the volume of these sets? So when M tends to infinity, A plus A divided by M, it tends to the convex hull of A. And so there is a hope, there was a hope that it would be true. And for A convex, of course, A of M is always equal to A for any. If you add M times the convex hull of A and you divide by M, you just recover convex hull of A. So it's stopped, and this is A. So this stops, I mean, there is no point, and this is obviously true. And again, so this conjecture is interesting only for compact non-convex sets. And yes, and so this is the theorem we had with Mokshay, Madiman, Arnaud Marsighetti, and Artem Zvavich. So we studied this conjecture, and we could prove that it is really increasing for n equals 1, and not necessarily increasing for n larger than 12. So just a few elements about the proof. It's true for in dimension 1, we adapted the proof of Leff and Garmati, Maltolci, and Ruja, who were studying the same kind of thing for discrete sets, and the same kind of manipulation combinatorics between to reconstruct an M set from the M-1 set we could build. And for n equal 12, starting for 12, we could build counterexample. And the counterexample, in fact, is very simple, but because it's 12-dimensional, it's not so easy to picture out. But this is a union of two squares, which are lower dimensional, you see, two cubes. So you take a cube, you are in dimension 12, and you take a 6-dimensional cube in one 6-dimension plane in the 12-dimension plane, and another cube in an orthogonal dimension. Okay, and you look at the union of these sets. So if you would do it in dimension 2 and take two orthogonal dimensions, this is it. And you look at the half sum and the three sums, you get these sets. So you see that you are starting to build to converge to the convex hull. You have more and more squares when you add, I mean, rectangles, these kind of things. And in fact, you can compute things not too difficult, and you can see that it's not increasing, it's going the wrong way for these sets. Okay, so we try to play a bit with this to replace by these cubes by rectangles, of course, and everything, but we could not decrease to dimension less than dimension 12. And so the question remains completely open, even in dimension 2 and 3, which is a bit crazy. But we don't know this. Later with, so we have also the same question that we had with Arnaud Marsilietti alone about this Costa cover conjecture, about concavity of entropy power. Do we have eventual monotonicity? So if A is fixed and M large enough, is it true that it is increasing at some moment? So for this, with Zolt, Lengi, and Artem, we recently, I mean, it should appear this year, and we did it 2 years ago. It is in the archive. We prove that for A star-shaped, the answer is yes in dimension eventually. So in a dimension larger than something which is like a square of n. And so, for example, this is too nice because it settles the conjecture for star-shaped sets in dimensions 2 and 3. So it's true for this. This is increasing dimension 2 and 3 for star-shaped sets. We don't know for connected sets, for example. So there are many things that can be asked. So this is all what we know. Okay. So now I go to other conjecture I have looked at and with co-authors. So there is another inequality, which is a bit the stronger inequality in this field in information theory, is a Blachman-Stam inequality. So again, Z is a standard Gaussian independent vector of X. The Fisher information, I already defined it for you. This was the derivative of the entropy. And the Blachman-Stam inequality states that for X and Y independent, the Fisher information satisfies this, the inverse of this Fisher information satisfies some concavity property. So inverse of I of X plus Y is larger than inverse of I of X plus inverse of I of Y. And so if you look at the analogous way I showed you to produce inequalities for determinants, or if you apply it to use this inequality for Gaussian random variable with some covariance matrix A and B, you get this Bergström inequality. In fact, not exactly this one, but so determinant of A plus B divided by the determinant of minor matrix, principal minor matrix, satisfies this inequality. Okay, it should be in fact with the sum of the determinants, but what is called Bergström inequality is this one. So here I put A1, B1, A1, B1, but of course it could be AI, BI because they play all the same role. And in fact, it's stronger than with the sum, because I recall that the surface array was like the sum. In fact, I of X is like the surface array divided by the volume. And also it's like the sum of these determinants divided by the determinants. And so the inverse of I is like this thing. And in fact, this is true, and it's stronger than with the sum. With this, you can pass to the sum by using some Minkowski inequality. It works, but it is reverse Minkowski inequality for -1 sums, and it works. As I recall that if you have Minkowski inequality is reversed if P is smaller than 1 strictly. Okay, and so in the world of convex geometry, Dembo, Cover, and Thomas defined so the analog of I, or the inverse of I, in fact, is volume of A divided by surface of A. And they ask, on the set of convex compact set, is the function J concave? So this is a C conjecture, let's say, or monotone. And we will call it the M conjecture. So the C conjecture saying that this is concave because it's one homogeneous. In fact, you see that if I put J of lambda A and lambda is positive, I just get lambda to the n volume of A here, and here lambda to the n-1. So lambda to the n-1 cancels out and only lambda stays. So it's one homogeneous in A. And so this concavity property is exactly the same as this, because I could put 1 minus lambda A plus lambda B. It could go out, and this is exactly the same as this. Okay. So is this concavity property does this hold? Or weaker inequality, just even this holds, the monotonicity. If I add something, a convex set to another one, is this ratio increase? Does this ratio increase? So these are very nice conjectures. And Bunsen, in fact, it follows from, so it's much earlier result of Bunsen, proves that, in fact, C holds. And even, so the monotonicity, the concavity property holds in dimension 2. And even a stronger conjecture, I mean, a stronger inequality, because we can divide just by volume of projections. So here I say volume, but of course it's a length, because A and B are and I wrote volume, I'm sorry, here I just copied back. I should put volume 2, which is area. So this is the area of A plus B divided by the length of the projection is larger than the area of A divided by the length of the projection, plus area of B divided by length of projection. And here, PU,
sorry,
yes.
Mathieu, so, excuse me. You're asking here convexity, right? In this,
yes, concavity.
No, convexity of the set.
Yes, convex set, convex compact set. Yes, here it's not for compact, it's not for non-convex sets, because anyway we don't know it. I mean, you will see.
Okay.
Yeah, you will see that in fact it doesn't hold for convex sets, so it's no point to ask. Yes, okay. So some inequalities, it's a bit strange. Some inequality holds or are supposed to hold for compact sets, some other for convex sets, and even for convex sets, some it's not true. So we need to assume more. You will see. So it's a bit strange, yes. Okay. So this holds, and in fact, this inequality of Bunsen, it implies inequality with a surface array. So here it's just perimeters. Because the perimeter, there is a thing which is called Cauchy surface array formula, which says that the volume of the surface of a set can be of a convex set can be recovered by the average of the volume of its projection on hyperplanes. Okay, and because of this, and again, Minkowski inequality for -1 sum, starting from this inequality, you get this one. Okay, so Bunsen solves completely this. It's true for any convex sets in dimension 2. And then, in fact, Dembo-Cover-Thomas, when they asked if this is true, they proved it for B2N. And Giannopoulos, Artsoulaki-Paouris studied this conjecture and proved it also with a different proof for B2N. So this concavity holds for one of the sets being a Euclidean ball, and by linear, it's also by linear. If you apply a linear map, it's also true for an ellipsoid. Okay, and with Giannopoulos and Meyer in 2003, we proved that in fact this conjecture is too strong, and it cannot. This one doesn't hold. Even the weaker inequality does not hold for all convex sets in dimension larger than 3. So it seems that it settles the inequality. In fact, what we did with Apostolos, Giannopoulos, and Mathieu Meyer is that we proved that an inequality with another constant that was proved by Giannopoulos, Artsoulaki-Paouris before was optimal. And the way we did it was a bit involved and using some limit arguments. And later, much later, in fact, Arstein, Avidan, Florentin, and Ostrover gave a direct counterexample for this inequality M. So which of course, because this is a weaker inequality, if you have a counterexample to this weaker inequality, this is also a counterexample for the concavity property. So it seems this is settled, but in fact, you can ask for weaker inequality. For example, you can ask the monotonicity conjecture that I asked. So I recall G of A was volume of A divided by surface array of A. We ask if this increase when you add a segment, so the original M conjecture was when you add monotonicity, any convex set B. Now I ask if this holds when you just add a segment. So this is clearly a weaker inequality, and we call it P because it's related to projections. So with Giannopoulos and Meyer, we prove that again, this inequality holds only in dimension 2 and doesn't hold in dimension larger. And Arstein, Avidan, Florentin, Ostrover proved that this inequality is equivalent to say that this G of A, in fact, increased by projections. Okay, so here, of course, you need to take G of PU perp of A means the volume in the hyperplane of PU, in the hyperplane U perp of the projection, and the surface area of in this hyperplane of this projection. So this is a comparison between two things which does not have the same, doesn't live in the same dimension. Okay, and with Madiman, Meyer, and Slavich, in a paper that we are trying to finish now, we prove more equivalences. In fact, if you have a convex body and you look at all its linear images, then checking this inequality P, which is equivalent to this. So this is what I copied back. For all these linear images and all vectors U is the same as asking this beautiful inequality that I like very much between volume of A, volume of its projections on a subspace of dimension n-2, which is intersections of U perp and V perp, and times the sinus of the angle. This is just 1 minus cosine square, so this is square root. So this is just the sinus of the angle of U and V. So this is the sinus of the angle of U perp and V perp. You have two hyperplane, and you look at the angle. So we ask if this holds. So the fact that this holds for all linear image of a convex body is the same as this, and is the same as saying that this volume, which is a polynomial, this is known because this is called Steiner formula, the volume of A plus S times a segment plus T times another segment. So this we know it's a polynomial, and this is the same as asking if it has only real roots. Okay, and moreover, with Madiman, Meyer, and Slavich, we prove that this is true. All this, because they are equivalent, this is true in dimension n for K being a zonoid. So what is a zonoid? I forgot to say. Zonoid is just Hausdorff limits of zonotop. And what is a zonotop? A zonotop is just a Minkowski sum of segments. Minkowski sum of segments is the same as saying it is a projection of a cube, in a smaller dimension, because a cube is just a sum of segments, and you projection of a sum of segments is a sum of the projection of a segment. Projection of a segment is a segment. So it's the same as saying these are projections of segments, of sum of segments. So also it's the same as saying that the all faces are symmetric, centrally symmetric, have a center of symmetry. Okay, so a zonoid is something which is very symmetric. And so this, as I said, we had proved before with Giannopoulos and Meyer that it holds for any convex set only in dimension 2. And now what we are saying here, it in fact for, if you don't look at it on all convex sets, but you look at it on strictly smaller families, like for example, zonoids, then this holds in dimension 3. And we conjecture this holds also for any dimension, but we cannot prove it for now. So for example, it holds also for the Euclidean ball. It's not difficult to check. Euclidean ball plus a segment, a cube. So we can look at many things. And if we can compute this, we can try to, Euclidean balls are zonoids. There are examples of zonoids. Okay. So Brunn-Minkowski-Minkowski proved that this holds also for the simplex. And this is linked to work of Brasitikos, Giannopoulos, and Yakopoulos, and Giannopoulos, Koldovsky, and Valetas, and David, Alonso Gutierrez, Shiri, Arstein, Avidan, so González Merino, Jiménez, Villa. So many people, many of the audience, so they worked and they proved generalization, in fact, of, so the last paper here is about beautiful generalization of this inequality 2, where you can replace these hyperplane projections by any projections on any dimensional spaces, which is very natural things to look. And so here, and they prove that you have, they found exactly the best constant you can put. And here, of course, there is something with which computes the angle between the spaces, and they could prove the sharp constant you have here. Very good. So there is a link with another question, which is called the Marcus question, and was asked to us by Guillaume Aubrin. And in fact, he asked if the Steiner polynomial, so the Steiner polynomial is just the volume of z plus t b2n. So this is a polynomial called Steiner polynomial in t of degree n. And if you have a zonoid, it was asked by Marcus if this polynomial has only real roots. And this is true if z is in dimension 2. And Katz-Nelson proves that, in fact, this is, he was not studying this, but we found in his paper, he was studying Steiner polynomial of many examples of convex bodies. And he proved that for n large enough, and z being some flat ball, PZ have non-real roots, but it answered Marcus' question only for n large enough. And with Madiman, Meyer, and Zavich, we could prove that, in fact, just inspired by this, also the proof was very complicated, but inspired by Victor Katz-Nelson idea, we just checked that for disk, flat disk, dimension 2 disk embedded in Rn, if you look at this disk plus TB2n, and you can just compute this volume, and you use Fubini, you can write it completely what is this volume, and you find that it has non-real roots. Okay, so it solved completely this Marcus questions, and the answer is no. And I want to go to the last series of inequality I have on convex sets and zonoid, and this is what we call together the three bodies inequalities. So again, it comes from the information theory, and it was proved by Madiman in 2008 that the entropy of the sum of x plus y plus z plus entropy of x is smaller than entropy of x plus y plus entropy of x plus z. Okay, and if you apply it for Gaussian random variable, random vectors with covariance matrices A, B, C, then you get this inequality for determinants. The determinant of A plus B plus C times the determinant of A is smaller than determinant of A plus B times determinant of A plus C. And so if you apply it to convex to random variables which are uniform on convex bodies, and you apply some Rogers-Sheffard inequalities, so some classical inequalities in convex geometry, you can prove that in fact you have volume of A plus B plus C for any convex bodies A, B, C. Volume of A plus B plus C times volume of A is smaller than 3 to the n times volume of A plus B. I forgot a parenthesis here. Times volume of A plus C. Okay. And so the question is, can we improve this 3 to the n? So the answer will be yes, and moreover, the answer depends on which set ABC you want to plug in this inequality. So to make it more rigorous, let's introduce this here ABC. This quotient, the constant you can put here, the best constant you can put here for ABC is of course this quotient. And Cn is the worst constant you can put, I mean the best constant you can put, which is valid for all ABC convex bodies. Here it's not written, but for ABC convex bodies in Rn. So from Bobkov-Madiman, we know that Cn is smaller than 3 to the n. And related to this, Thomas Courtade is working also in information theory, and he asked the following question in 2016. Is it true that if I plug here A is B2n, so the Euclidean ball, so B2n, 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 so you see you repeat, or epsilon B2n, it's a bit the same, because you can put the epsilon on the other thing. So you are looking at neighborhood, again, epsilon neighborhood of sets, and the volume, does it satisfy this inequality? So it's again some concavity, strange concavity property of the volume, and this he asks if it's true for any convex set B and C. And this, for now, we don't know yet, and it's clearly annoying. So what we could prove with Madiman and Zvavich about this conjecture, we could prove that, in fact, this inequality, this is a bit strange, but the fact that the inequality holds, so the M inequality for zonoids, so the M inequality, remember, was the monotonicity inequality for zonoids. So monotonicity means volume of A plus B divided by surface array of A plus B, is it larger than volume of A divided by surface array of A? So this conjecture, if it's true for every zonoid, it's equivalent to say that this inequality holds for every zonoid ABC with constant 1. It's equivalent, and in fact, it shows that this cannot, I mean, yeah, okay. So it's true in dimension, I think I say it later, but it's true in dimension 3, for example, because we know this inequality in dimension 3. We know this inequality in dimension 3. This one also. Okay. Also, we proved, and so Artem Zvavich told you a lot about this when he came to your seminar. And here, since we have worked and we have found better inequalities, so we have proved that. So in dimension 2, it's true, and it comes from, in fact, Bunsen inequalities that I gave. In dimension 3, the best constant is 4/3. In dimension n, in fact, we have a lower bound, which is 4/3 to the n, and an upper bound. And this is amazing that we found the golden ratio here, 1 plus square root 5 over 2 to the power n. And we found it very recently, and we are very curious to know why this golden ratio appear here. It's amazing. Is it the best constant we can have? I don't know. So for now, the best, I mean, asymptotically, because we know the best constant, for example, in dimension 2 and 3, and there are this, and this is not the same as this. But maybe when n tends to infinity, this is the best, but we don't know. I mean, we need to understand better these things. And also another thing we can do is related to Courtade questions. So if A is B to n, this was a Courtade question, we know that it's true for B being a zonoid and C being any convex body. So the answer to Courtade for the moment is yes, if one of the body, B and C or C, is a zonoid. And also using a previous result of Sopunov and Zvavich, it's true for the simplex in dimension 2, 3, 4. And so we expect that it will be true also for the simplex always with this constant one, but we cannot prove it. So many things we can prove. We can still prove also many things. And nice things, I think, with this golden ratio. And I think this is it. Yes. So thank you very much for listening. And if you have any questions.
Okay, thank you very much, Mathieu. Are there any questions from the audience? You can unmute yourself and ask.
Thank you. I have a question I think appear a couple of times, but what in the real roots of the Steiner polynomial, when the main example was a flat, okay, because sometimes
yes,
I'm used to convex bodies with full,
yes, convex body. Yes, yes.
With interior. So I guess if you change this flat convex body, but something a little bit thicker, does it work to make it non-empty interior? Or
I understand. This is a very good question. I think yes, it will work. Yes, I was thinking yes, because yes. because it has complex, I mean, the maps, which there is some continuity here, of course. So if Z is close to, if you have a sequence, I mean, if you have bodies which are close to each other, of course, the polynomial coefficients are close to each other. So now you need to understand what happens for the roots. And of course, the roots also, there is some continuity arguments. And because you have complex roots, which are real complex, I mean, non-real, and so it will work. Yes.
Okay.
But we haven't written it. Yes. Maybe it's not so difficult also to go to see what happens if we thicken a bit this even by a cylinder. What happens? Yes, we could try to compute it. Yes. But just the limiting argument, I think it's
okay. Okay, thanks.
All right. Are there any other questions?
I have a question. First, hello, Mathieu.
Hi.
About well, the question is very general, but for example, for the last slide, when you talk about the three bodies.
Yes.
Have you think about the problem, the extension to the functional extension to these kind of inequalities?
Yes, exactly. Yes, we are doing it also. Yes, with Mokshay a bit. So we had the problem. So this is a very natural thing to do. Yes. So in fact, there are two, in a way, you could say that this entropic inequality is some functional extension. So there are two kinds of extensions of functional extensions of inequalities and convex geometry. There is a one which goes to information theory, and the one which goes to inequalities like Prekopal-Heinler inequality. Yes. And for the one with Prekopal-Heinler inequality, we are doing it. Yes. The problem, the main problem for us was to understand what is zonoid functions. So because in fact we did it at some, I mean, we tried, because there is this thing with for example, for Malheur conjecture, with Mathieu we had a long time ago we studied Malheur conjecture, functional forms of Malheur conjectures, and Malheur conjecture is known for zonoid. And so it was very natural to try to prove it. So we extended what was known for convex sets to functions. So for example, in conditional functions, it worked, the Malheur conjecture. And the question to prove it for zonoid functions was natural, but we could not, I mean, we could not find not nice enough ideas to generalize, to define zonoid functions. But now with Mokshay, we have found it, and we think we can do it, yes. So okay. This is a hope for doing much more inequalities, yes, for this, yes.
Okay, thank you.
You're welcome.
All right, any other questions? No, I have a question about the conjecture which was false when you were adding copies of the same compact sets and dividing by the number of copies.
Yes.
I don't know what the conjecture or the problem would be, but what about considering adding the rotations of the convex bodies of the compact sets? Because in that case, I don't know, if you have a convex body, this way you are not modifying the convex body. But if you consider the proper rotations, you will be converging to a ball. Like in the case with the random variables, where you would be converging to a Gaussian random variable.
Yes, 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 yes. So you are asking if I do a sum with different rotations?
Yes.
Yes, 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 yes. Why not? What happens? This is a good question, and I don't know. but this is a nice question, yes.
Okay, so maybe you need a different normalization, because if you consider the volume, you would be tending to the volume radius, but I don't know. Just
Yes.
something.
Yeah. No, but it makes sense. So we haven't considered this at all, this for sure. And even, so for example, I haven't said, but here, this is a good time to say it, I think. If you look at the subsequence, instead of looking at all of the whole sequence, when you look at all A of M, all M copies of A that you add, if you look at the subsequence 2 to the N, 2 to the M, so you look at only of power of 2s, then this holds, this increasing, because it follows from Brunn-Minkowski inequality. Even if you have compact sets, it works. So this, you know that it's true for this subsequence, and you don't know for others. So for this, because you can compare A plus B over 2 and A and B, okay? Or A plus A over 2 and A, okay. And for your question, so the first question would be to understand what happens just if you add two copies. I mean, yes, volume of A plus a rotation of A, what happens? Yes, so this is yeah.
Okay.
Good. Let's do it. Very good.
Okay. Any other questions or comments? If no, then thank you again, Mathieu.